board, the starting point is the chip. So, chips depending on the technology and all that, the I think correct me because of this gray. I have read about 120 as being the normal thing like that, but now very high temperature chips are being made, I understand, which are all 230 degrees centigrade and all they can tolerate. You can look it up, and if I have time in the end I will show you, but typically a chip can withstand up to about 120 degrees centigrade, but not continuously peak, and then anything above that, that is the end of it, and reliability comes down. So, if you see very carefully here on top surface of the chip, obviously heat can be taken away. You can mount a, I do not know, heat spreader and then do what all you want to do, and then bottom of it also, occasionally you have this bottom of it which is, there is heat coming here, and then you have seen the very interesting thing through the leads. Lot of heat is conducted away through the leads, and then where it is hot, more flux is there, and then the flux reduces, and then depending on the, what do you call, the physical profile of it or the footprint of it, the manufacturers themselves suggest what should be the pad footprint, how should the pads look like. If you follow all that correctly, you will be able to make things. So, what happens typically is the conduction is the predominant thing from package to enclosure walls. That is how the walls get it, conduction from a heat spreader to enclosure walls. Sometimes the packages are directly mounted on the wall, or you need a heat spreader, typically a bridge or something which I have shown you earlier, to enclosure walls. That is, you mount all these things on another small thermally conductive plate, and then bolt it onto the enclosure, and then conduction directly from PCB to enclosure walls. So, in the case of certain aircraft equipment and all that, the PCB edges, if this were to be a PCB, the edges themselves are made with, copper is kept thick places, and then it goes into a mount, and then it is clamped there like that, and some of them are made with metal core. We have something called the thermocore PCBs where the metal core is there. So, as the flux densities keep increasing, we need to play on all these things. So, coming back here, we have this convection from internal ambient to enclosure walls. So, the inside the enclosure things are hot, they will be about maybe 70, 80 degrees hot. The heat inside itself is not everywhere, but there will be internally what do you call thermals which are there, which will do the convection. So, from the PCB heat is picked up, the hot air, it cools on the wall, and then it comes back. So, we have this convection. Sometimes to prevent hot spots from building up, you may have a fully sealed enclosure with a small recirculating fan inside, that ensures that all the heat inside the enclosure is smoothly circulated, and the wall itself may have fins inside, we may have fins inside and fins outside. So, if you have typically a wall like this, it is possible for it to have fins on one side, similarly fins on the outside. Fins on the inside pick up heat from there by convection, as I said, by having a fan inside, fins outside transmit it outside. So, this you would have seen in commercial literature related to air conditioning. The air conditioned outdoor units and similarly the evaporator indoor units are often made this special finned tubes which have fins inside and then fins outside. So, we have an advantage there because we have the working fluid circulating inside and there is a high powered circulating pump inside. So, the fins will not impede the flow of the working fluid, and depending again on the design and all that, we can make them of the correct profile because most of the times the fins are extruded. Similarly, on the outside also the fins sometimes are attached to further the tubes are attached to further fins or the fins are directly extruded. So, if you get a chance, have a look at a old outdoor unit of a air conditioner, especially the split air conditioners. There you can clearly see the main copper tubes are something which are attached to the fins, which happens to the that device you see in the front of the car, the heat exchanger which is kept there. So, again there across the wall we have conduction and we need to analyze the conduction, and from the working fluid to those what you call those fins, the thing is by convection. Here slowly the concepts of heat and mass transfer will come to you. Oh sorry, let me go back. This is one of those beautiful simulations. For some reason it is not working because I think flash or something is needed and it is not enabled. So, you can go and check on the internet. You see there these days there are commercial software that are available which will help you understand this. Other than the what you call extreme expense in acquiring one of these software, the other issue is also about how well you model your component and your system. So, it is obviously a two-step process. In the first step you have a rough prototype and you need to estimate instead of being completely like a what do you call enthusiast or I want to avoid the thing by a mechanic. Mechanics are much better than me. I can talk and they can do lot of differences there. So, unless the person who is actually on the field who does it just by trial and error, you can always put together a simple prototype and then after carrying out this analysis you can optimize it. And while optimizing you can, if you see, you remember that fins, I showed you that cooler, one of them that fins are not strictly radial, they are all also following a peculiar what you call tangential, like a curved fins like that. In one of them the fins are radial and then the heat is being taken away like that. These things can have come out of optimization using these our software. The next picture shows you unconventional things which are not used often, but they are also used. The thing is they have practically become proprietary, and I think all of you know about this heat pipe, how we have a wick, how we have a one end of it. Though I will repeat it again, such a beautiful picture, I myself am caught in this. So, invariably there will be a long tube, hollow, it is not a solid. The comparison is always between the solid tube and the hollow tube. So, in this hollow tube the main components are, there is a wick which is close to the wall here, a thin wick, maybe a millimeter or so. If you take an 8 millimeter tube, the wick may be only 1 or 2 millimeters, and then on one end of it this is attached to the heat generating device. You remember that as some this thing that aluminum, this copper things are there. For the case of convenience it is, in the case of analysis they have shown it as a round tube. So, the moment you give it to heat, phase change occurs here. that liquid inside starts becoming vapor, and then we have a latent heat of evaporation similar to what will happen when we boil water, which is common practice. If you are to put water in a vessel and start boiling it, you will notice that the water evaporates by surface, some boiling, and all the bubbles escape and vapor is generated at the surface. And then the origin of the vapor, no, maybe some because of nucleate boiling, and we have that famous experiment and all that, no. The vapor bubbles will start at the probably bottom or wherever it is and come out, and the issue there is latent heat of evaporation carries away all the heat. Temperature of the liquid does not change. Commonly it is used in various things like a milk boiler. Water generally, no, it is taken that water boils probably depending on the ambient and so on around 95, 97 up to 100 degrees at sea level. So, in Bangalore, we are at a elevation, it boils at a what do you call lower temperature. I take it that our water boils at 97 degrees, but milk requires a little more than 100 degrees for boiling over. It forms that casein and then the whole thing comes. So, if you take a water jacketed vessel, that is you take water in a vessel and then put one more vessel inside, put milk in it and start boiling the water inside, it will never reach the boiling over point of milk. This is how typically a water jacketed vessel works, and what is called a milk cooker also works. And now, do we need to boil over the milk? That is a thing in, we have been taught as children, no, it must. You stand there, watch and boil over, which is probably how the steam engine was invented. When a child was asked to what you call do anything, he did the next thing. What did he do? He pressed on the cover. And one small thing what we miss is, if there is a spout, it would not have developed a pressure. Probably it is a closed vessel. Then only found out that if you close it, the pressure builds up and so on, and then after that now things have improved dramatically. We probably are not interested in it. But the starting point is the boiling that takes place here. In the case, the phase change occurs here, and then pressure also builds up. As the pressure builds up, it tries to what you call push all the vapor to the other end, and the other end is cool, okay, because they have put fins here, and then depending on the working fluid, usually they have water and propylene glycol, and then probably they evacuate it also a little, and then other types of what do you call alcohol which boils at a lower temperature. Probably most of the times they use propane 2-ol, okay, isopropyl alcohol. It boils at much lower temperature, not propylene glycol. Propylene glycol is for something else. So, when they take this what do you call propylene, isopropyl alcohol or anything, the boiling point may be around 50 degrees centigrade, 60 degrees. So, at that point it starts boiling here, and then when it comes here, when the ambient is say 50 or 60, it will start condensing here. Two things have happened. When it condenses, a lower pressure, the pressure falls down. So, we have something which is pushing here, something which is what you call sucking it out here, and then the condensation is returned by wicking action back. So, again I am sure all of us thinking people will have the question, does it work in all orientations, what are the critical things? These are all things which people have worked on very well, and then there are commercial samples. If you just check on the internet, you have that thing. The best example is, you have a tube which is probably 200 mm and then around 8 millimeter diameter, 200 mm, and then other side you have a copper rod. Put both of them in coffee and you can feel the difference. Okay. Obviously, the heat transfer rate and the flux here can be made to be 10 to 20 times that of a solid rod. Both of them are made of copper, one is copper tube, and they have made other inert materials. So, the next one, this is what I was telling you about. What looks flat, I mean things very convenient there, is not that easy. In actual modeling, you see here 2 or 3 things are there. Here once again, while the inside is very exotic, and then you have a small what do you call a device to it is a soldered nipple, that is after evacuating it they crimp it and then they also fuse it by something by which they know what is the total material and all that, and then we come back to the original thing. From here to here the mechanism is conduction. In this case you have a probably it is a magnesium zinc aluminum casting, and then on the other side you have copper. So, from various places including devices here and devices underneath, and then you have seen this small thing is a strap. In this case we have 3 clamping screws, but in this case there is a solid strap. So, you need to unscrew this strap and then clamp it. It is clamped, and these 2 are already fitted in the factory. They are probably swaged or otherwise forced in the factory, but main mechanism is conduction, which is the reason why it has been included here, and it goes back into the device at the back, which is the where the condensation takes place, and then that exchanges the heat with the ambient here using convection. So, internally you have convection, and then outside you have this beautiful convection again, but between these 2 conduction seems to be very, very critical. Same thing even if you were to take a laptop, this is a little old, very critical component is this heat spreader. This heat spreader takes all the heat of all the components and then tries to push it inside and makes, I am sorry, it will try to collect all the heat and push it outside. And then if you take an average laptop, you only have the top surface and the bottom surface, and in the bottom surface these days if you actually put it in your lab, chances are not comfortable. So, you also have a fan, a small tiny fan which is probably kept an angle depending on the various things. I do not know how the very thin laptops are done. I suggest go to Tech Republic and see how to open various new devices. It will show you how things are done. So, you have all those devices. Now, this is taken from what do you call sensor installation, which I have worked with my colleagues. So, you have here, do you see, typically I am sure you have seen such things outdoors as part of weather collection. So, I do not know what are the sensors inside, but all that I know is they should not gather heat. So, in this case they have reflective shields everywhere to ensure that the solar radiation does not heat up the components inside. So, some of these come with fins and all that. The fins have the property of giving away what do you call air by convection, not picking up anything by radiation, and also they allow in guiding the air to cool things. You see, we have something here, and then we have all these antennas, and then in the place where we work we are in a slightly remote place, so we end up with having batteries. Okay. So, you see here this whole thing is an aluminum case. I think probably this is the last slide. Now, slowly we are coming into the future. The future is passive components in organic substrates with embedded components and high density interconnections. If you see the slides here, you see here fantastic high heat flux cooling. I am lucky. We have Siemens what do you call system on chip, and then we have so many of the thing, wafer level packaging and heat flux cooling, which uses the other thing. This I have taken from my colleague in DSC who works in the interconnection area. It is not the future, it is the present. Already such things exist, though the what do you call, it is not as common as you can think of. So, things have progressed tremendously. While I talked to you about the phase change, what do you call, heat pipe and all there, here you see already there are devices which have this phase change things built on top of it, and then they are able to take away heat at a high flux. Let me come back for this what do you call, what I showed you already here. All these active components and all are directly mounted on a heat sink which projects out. So, we have conduction and we have everything we know about it. Now, you see here other place, this one is some temperature compensated some pressure device. So, you have a pipe here, and then that we have that pressure thing here, and then there is a temperature sensor here which makes sure that the compensation takes place, and the whole thing is sealed in a space grade enclosure, stainless steel in this case. And then we have all the beautiful electronics which is built inside, and we have one simple coaxial connector through which it is expected to receive what do you call, all the power, and then also expected to, we have a small orifice here which takes care of the other things. We had two what do you call, serious researchers here who have worked in the place where I work. One Professor Schoenholzer was with us way back in the 80s, who is from, I am not sure, I think he is from New Technicum books, NTB in Swiss, and he has written a small what do you call thing here, which I have scanned them, and this being CDT property, and then he has what do you call, permitted us to use it. The table of contents, you will notice here now, it invariably starts with introduction similar to what I have spoken, then conduction, convection and radiation, and then something which I was talking about. Finally, the next slide is going to take you to something which we both like and we do not like it so much. So, very simple thing is, how did we come about to these correlations? You understand, no? Generally what is heat transfer and how did these correlations come about? If you break them down, which will come to finding out temperature of a source, temperature of a what do you call, a sink, and in between how to find the transfer coefficient. And then while the heat transfer coefficient is known, physical parameters like the physical dimensions in the case of conduction, area of cross section and how it varies, and in the case of convection, the surface area that is required, and rarely in the case of radiation, what is the area that is exposed to the source, from the source to this thing. So, we all know sitting in the shade is cooler than standing in the sun, but then remember sun is at a very high temperature, we are not that hot. So, starting in the next lecture, I will what do you call, try to, I will not say read out from here, see as well how I can explain these things. So, my suggestion is kindly go to the NPTEL HRD lecture series, go for simple heat transfer. Heat and mass transfer is a little complicated, simple heat transfer. In that things like this conduction formulae and how they have come about are already explained by the other lecturers. For the purposes of continuity, I will be talking to them here. And then you can also go to the look up on the internet, because these are all relatively very simple and okay. Things like this is what the other slide which I have shown you in the beginning, taken from the YouTube link. Everybody talks about B is equal to small this thing and so on like this. And the only problem is, where do we get this K? It is dependent on the situation, it depends on the not just the material, the condition of the material. Is the what do you call, material heat treated, is the material extruded, is it what do you call, how compact are all the the particles inside. It is a very specific characteristic at that point of time. And finally, conduction only talks about one place to the other place, and then everything else needs to be mounted on it, no, a chip needs to be mounted, and then similarly heat spreader needs to be mounted inside. So, two things, one is the material, and then even a very routine thing like our aluminum. I think I am sure all of you are bicycle enthusiasts. When people talk about 6000 series and 7070 bike and all that, you know it can be complicated, and there are a lot of material on the internet which you need to study carefully. You can't say aluminum is lighter, saying 70 some 65 is stronger like that, no, you need to see various other things. So, two things we do not know here is, while this area of contact and the temperature coefficient in conduction, both of them we are not very clear. However, we have guidelines, if you go to the catalogs we can easily get it. So, permit me to stop here and start in earnest tomorrow and try to see how I have understood it. So, thank you, we will meet again.